Okay, so good morning, good afternoon, and good evening, everyone, depending on the location. This is Koji Yamashita, the moderator of the webinar from UC Riverside. Welcome to the RTPS Foothills section webinar. Our Foothills section covers a wide geographical area stretching from West Covina to the eastern end of California, and from Temecula to Baker. We are honored to have an esteemed IEEE Fellow, Professor Nicholas Hadziariu from National Technical University of Athens as our speaker today. Thank you for joining us. Before starting the presentation, let me introduce the speaker. Nicholas Hadziariu received a diploma in electrical and mechanical engineering from National Technical University of Athens in 1976, and an MSc and PhD degrees from University of Manchester Institute and Science and Technology UK in 1979 and 1982 respectively. Since 1984, he has been with the Power Division of Electrical and Computer Engineering Department of National Technical University of Athens, and since 1995, he has been the full professor in power systems. Since 2015, he had led Greece's electricity distribution network. Prior to that, he held an executive role overseeing transmission, distribution, and research in the country's power sector. He is a past chair of IEEE Power System Dynamic Performance Committee and past chair of SIGRE Study Committee C6, meaning Distribution Systems and Distributed Generation. This time, he also briefs his SIGRE C6 working group regarding batteries. And he is co-chair of EU Technology and Innovation Platform of Smart Networks for Energy Transition. He has participated in over 60 R&D projects funded by European Commission and others. He has the editor-in-chief of the IEEE Transactions on Power Systems and a member of editorial board of IEEE Transactions on Sustainable Development and the IEEE Power and Energy magazine. He has authored a textbook, over 200 journal publications, and 500 conference papers, and was listed among the top 1% most cited researchers in 2016 by Thomson Reuters. So impressed. So as you know, that Nikos is a world-class expert. Well, Nikos, fire away.
Thank you very much, Koji, for this very kind introduction. And I'm very happy to be with you today. I know, Koji, you have collaborated in the SIGRE in a batteries task force. I'm going to speak about it for a very short time. But the main topic of my presentation today is about frequency dynamic unit commitment for isolated systems, and especially how we can apply data-driven techniques for such problems. So what I'm going to talk about in the next hour is a few words about what are the non-interconnected island systems, the role of storage, how you can apply data-driven techniques, especially classification techniques, classification trees, how you can use these rules for formulation of unit commitment with frequency dynamic constraints. And then I'm going to speak about real application and the use of a digital twin that uses these structures, and finally to conclude. So the characteristic of islands is that they are mainly supplied by autonomous power stations that are running on light fuel or heavy fuel with high operational costs. And although there is normally very high renewable potential, there are several constraints imposed, mainly for frequency stability reasons. Regarding Greece, Greece has quite a large number of islands, several hundreds of islands that are actually grouped in a number of groups, and now they are 28 isolated groups of islands and one isolated system like Crete. They host 15% of the Greek population, and they account for almost 14% of the annual electricity consumption. At the moment, there is quite a high effort of the TSO to interconnect the islands. However, some of them will still remain isolated because it's economically unprofitable to do this project. So there are always interest in islands, especially because islands with very high penetration of renewables behaves as the even interconnected systems with very high penetration of renewables will behave. So the frequency stability is the main security concern in these islands, especially when you have a very high renewable penetration. The already low system inertia, because there are small systems with limited number of rotating generators, is further reduced because the power electronic interface units replace the thermal generators. And as a result, there is a frequent and severe power imbalances causing frequency transients, mainly due to the high variability production of renewables, and also the high probability of disconnection of units due to voltage shocks that exceed the ride-through capabilities of wind turbines, also increased wind speeds that exceed the wind turbine cutout speed and can disconnect renewables. And in fact, there is the dynamic behavior of the system changes, especially when you demand that the inverter-based generators also provide ancillary services. In fact, storage plays an important role in these island systems. And here I take the opportunity to introduce very briefly the work that was done in the context of the SIGRE Study Committee C6 that dealt with distributed energy resources, dealt with battery storage and distributed energy resources in the distribution systems, where I had the pleasure also of collaborating with Koji. And here what we really did was to look at several use cases at the various levels of the system. We focus on the distribution system, and it's not very much in the scope of today's talk, that I'm not going to expand on this slide, but it really describes how batteries can the role of batteries in markets, in TSOs, DSOs, in the industrial installations, in front of the meter or behind the meter for DR and for operators and aggregators and buildings. And as you see, frequency control is one of the main applications, main use cases, and this is what mainly I'm going to talk about here. And in this report, there is a categorization of the grid support services, considering also the economic considerations, because batteries, of course, are still quite expensive, so the payback is an issue, and how in providing grid services, perhaps service to multiple stakeholders makes sense. And then how there are services to the distribution system operator and transmission system operators directly or DSO enabled, and how the battery outputs regarding active power and reactive power can be provided. So these issues, especially concerning the distribution system, plus other topics like the batteries' operational characteristics, some distinct use cases where the aggregation of batteries is important, the current regulatory regime, and also several regulatory issues and market issues are described in this brochure. So I'm not going to spend much time here, and I will go back to the island systems, where in this system, as I said before, if you speak at the current levels of very high RES penetration scenarios, at least this is what is aimed today. I mean, very high RES, I mean in more than 60, 70% RES penetration. Then you have the small overall inertia of the system. So the inverter-based units must provide frequency support. And when you have frequency transients, in extreme frequency transients, then the frequency relays disconnect load, and they can also disconnect the main relays, the remaining synchronous generators. So several grid codes demand that inverter units operate in order to provide primary frequency support, as you see in this slide. And in fact, also there are several countries that also demand enhanced frequency response ancillary services, like in UK. And the question is if these services are sufficient for frequency control in inverter-dominated islands, or if inverters could offer other services too, like inertia emulation. And in fact, taking some actual island cases like the Astipala Island, which is a small island that operates with diesel, batteries, and wind turbines. And it aims at very high RES penetration levels, as high as 73% of the annual demand. So studies have been performed on this island that when the wind turbine producing this nominal power is disconnected due to very high wind, the diesel generator and the BESS unit provide the power reserves after the transient. And what happens if the battery unit operates under the classical droop curve, providing reserves less than a second? So the studies have modeled this primary frequency control with a control loop that implements the droop curve and the first order transfer function to emulate the different time responses. And you see that according to the response time, how the frequency changes depending on the response time of 1 or 0.5 seconds. In fact, this is opposite, okay, because you have a drop of frequency since you lose the largest wind turbine. And then by looking at this transient, you see that even with fast response of 0.5 seconds by the battery, the frequency decays less than 49 Hertz, which means that under frequency load setting relays could operate in this case. And also, if you look at the rate of change of frequency in the lower diagram, at the beginning of the transient, again, you can see that the frequency can exceed, the rate of change can exceed the threshold of the loss of main relay generators. So this would lead to a further disconnection of generation units. So this is one particular case where it seems that you need to do more than just providing faster frequency response. And here is what, and of course, all this severe frequency decay and the rate of change of frequency is due to the lack of inertia. In order to apply faster response, you emulate the inertia of the system. So you can add another control loop that emulates the virtual inertia, as you see in the block diagram. And the results are in the diagrams where this function, the droop plus the virtual inertia, the response of the battery is much faster. That's regarding primary control. That, as you see also in the slides, it improves significantly both the frequency nadir and the rate of change of frequency too. Yeah. Another way to do this is to apply flywheel storage to increase the system inertia. That's also something that has been tried in some islands. Also in secondary frequency control, when the frequency is stabilized after a transient, the secondary frequency control starts to bring frequency to the nominal value. And here the issue is if you will allow the battery to provide secondary reserves, especially when the diesel units cannot restore the frequency in a high renewable scenario, because they are not, they don't have the capacity to do so. So in the lower part of the graphs, you can see what happens to the frequency when you don't have battery secondary control by the battery. This is the blue curve compared to the brown curve that brings frequency to the nominal one. And I mean, when the diesel does not have enough capacity to restore the frequency to the 50 Hertz. And then also how the battery output behaves and the generator and the diesel generator behaves in these two cases of control and no control. So that's as far as batteries are concerned. Now regarding the basic problem of dynamic security concerns, as we said before, frequency stability is the main security concern. We have the decline of system inertia. You have frequency severe power imbalances. So you have new operational characteristics due to higher rest penetration levels, less inertia, reduced primary reserves. You have interface-based generators that could provide ancillary services. And all this means that you need new security rules to operate the isolated systems. And when I say new, I mean that already now you have current security rules that are based on basically they restrict the penetration of renewables. So renewables, especially wind farms, are subject to power limitations, first because they need to keep a number of thermal units in the system, so they have to respect the technical minima. There's a dynamic penetration level limit, which is applied for stability purposes. Basically, this is again a static rule of 20 or 35% of the total demand. Also, the primary reserve levels are specified according to each island characteristics, but they are static levels, and they are normally conservative and do not guarantee the frequency stability, as you will see next. More modern current approaches for dynamic security is either to apply analytical approaches or data-driven approaches. For the analytical approaches, you can represent the frequency dynamics with the classical swing equation. You can use simple models for the generator's responses. Based on that, you can extract linear rules for steady-state frequency and rate of change of frequency. And then, once you extract these nonlinear equations, you can use them for unit commitment. And so when you commit the units, you theoretically guarantee that your frequency security will be preserved. Alternatively, you can use data-driven approaches, which mean that you create a database with dynamic simulation of system disturbances using detailed models, then using supervised machine learning techniques like decision trees or other classifiers like neural networks. You can apply these rules in the unit commitment problem. A few words about the analytical calculation. The classical swing equation, system inertia, change of frequency, the load damping, and then you have the response of the thermal units and the inverter-based units. And this is the disturbance magnitude. And what is important here to observe on the right-hand side is that these two types of reserves, thermal units and electronic-based units, have different response times and different response, different speed of response. So TS and TG are the times when they reach their available reserve, okay, the reserve modeling. So based on this equation, you can easily calculate the basic parameters that define the frequency behavior. So one of them is the steady state frequency, which means that after the disturbance stabilizes, which means that the delta f of dt over dt is 0. So that at the time after the TS and TG, you can assume that you have exhausted your reserves. And based on that, you can find the steady state frequency, which can be linearized and be used as a linear constraint of your unit commitment problem. Similarly, you can find the rate of change of frequency, which happens at t equals 0 immediately after the disturbance. There you assume that your reserves have not been mobilized yet. Then the delta ft equal to 0. And again, by solving this equation, you can linearize the problem of rate of change of frequency. So it is as a function of the disturbance of your and also of your system inertia, it can be used as a constraint in your dynamic in your unit commitment problem. And also, this is a bit more difficult, but still possible, to calculate the frequency nadir. This is the time when you have a time after the reaction of the power electronic units, while the others are, the thermal generators are still at an immediate state. So it's somewhere between the TS and TG. And there you can find again the frequency nadir using this equation, which is of course nonlinear, but you can linearize it piecewise and use it again to as constraints in your unit commitment problem. This requires a number of auxiliary binary variables, makes the problem a bit more complicated, but it's still possible in any way to linearize the security rules and use them as constraints in your unit commitment problem. Regarding data-driven approaches, they have the advantage that are trained on detailed models of the system dynamics in a number of training scenarios. So you should choose scenarios that are close to the critical conditions. And then by using supervised machine learning approaches, you can again define rules that you can apply in the unit commitment formulation. This is still not very much applied in practice, but it is possible and provides, as I said before, secure unit commitment plans. Yeah. So how this happens is you specify the critical scenarios, the commitment of generators, renewal penetration, primary reserve levels, what defines a critical scenario. You perform economic dispatch to obtain realistic generation reserve levels, and then you run your and then you from the dispatch solution you get the attributes for every scenario, the attributes that affect the frequency security, perform dynamic simulation, and for each scenario you obtain the metrics that classify frequency security that are, as we said, relative stage of frequency, frequency and adherent steady state frequency. So these are now the values that define the frequency performance of each scenario based on detailed models of the power system. And then you can use decision trees that are quite common already. It's a commonly used data-driven technique based on the entropy of the information or the information gain. And then based on that, you can derive if-then-else rules that describe the security boundaries. And using these if-then-else rules, you can transform them to the constraints that can be used in your optimization using several known techniques with big M, etc. Well, these techniques are perhaps have been applied, I remember, more than 20 years. You applied them also in island security constraints, but now the problem is that they can end up with quite large structures that are then too many rules, difficult to apply in a unit commitment. So there have been more advanced now classifiers like optimal classification trees. The point of the decision trees is that they decide locally in every node whether to grow or reduce their size. They do not consider the overall performance during training, and their results are normally suboptimal, and it depends a lot on the pruning of the size of the decision trees. While the optimal classification trees, they train the decision tree in one step. They're based on optimization function that you see on the right-hand side, where they minimize the classification error and also the depth of the tree. So you have an objective function that considers the balance between training accuracy and tree structure complexity. And the most important feature of that is that they, instead of if-then-else rules, they provide hyperplanes as rules that increases the accuracy. Of course, there's a drawback that you need to, that it takes much longer because it solves an optimization problem with numerous constraints. However, since this training is performed offline, it's not really a problem. So in this case, we have now tested these structures in an actual case of this is the second largest island in Greece called Rhodes. It has two thermal power stations. It also has a high voltage line. This is a 234 megawatt system that runs again on oil. It has a renewable generation of PVs, 17 megawatts of PVs that are dispersed at the distribution level, and 49 megawatts of wind power, 5 wind power plants. There is a characteristic of islands that they have high seasonal variability. So during summer, when there is also a lot of tourism, we have more than 200 megawatts of peak load. During winter, it can be as low as 40 megawatts. And the island faces several problems, both frequency and also voltage. So when power production is usually restricted for frequency dynamic security, a lot of wind, more than, I think it's now it's about 30% of wind power annually is curtailed. And in these studies we have performed, this is not at the moment used for advanced frequency services by the wind turbines. So we have used this now in our simulations, and we have emulated static inertia, fast frequency reserves, etc. So using a detailed model of the system, we have performed 2,000 simulated scenarios of critical operating conditions. We have used 75% of them for training, 25 as test set. And the results of the dynamic security assessment are shown here. You can see in the first in the upper graph that using the optimal classification trees, you have an accuracy 99.6%, independent of the depth of 1, 2, or 3 leaf. You have a very good accuracy. While with the classical decision trees, you need to go to a much higher depth to reach an accuracy of 93 point.
Nikos, are you online?
I no longer see his slides.
Yeah, I think he is disconnected for some reasons. So just wait for 1 or 2 minutes until he will be back. Thank you.
Oh.
Nikos, I think now I can see you again.
Sorry, my system was kicked me out for some reason. I'm back now, so just let me find my presentation again. I'm sorry about that.
No worries. We saw like the accuracy of 99.6% graphs. That
Yeah.
slide.
Sorry again, I think we are,
Now I can see the slide.
Yeah.
Yeah, please go on.
Okay, thanks. So it is clear that compared to the classical decision tree, we have a much better performance. And then if you look at the accuracy comparison, if you compare, for instance, the optimal classification trees with the other approaches, the decision trees, if you look at the overall accuracy on the right-hand side, you see that the optimal classification trees have the best performance, 99.6%, decision trees 88.8%, analytic 65, and by analytic I mean using the analytical relationship, as I described before. And the conventional is when you use static limits. It's clearly better than all of these the other alternative technologies. And in fact, the conventional techniques that we normally use today, although they are relatively okay regarding the classification of insecure scenarios, they're very conservative, and they are very bad in specifying secure scenarios. They think that the secure scenarios classify them as insecure at a very high rate. So they are overall unacceptable. Yeah. And okay, sorry. And regarding the results of the unit commitment solutions, you can see that running 100 scenarios for different wind power and load, you have used the unit commitment, you have run unit commitment for the same disturbance, which is the largest wind turbine outage, using the detailed dynamic model. And again, you can see that regarding the frequency nadir, the conventional approach is generally, of course, more conservative. Despite that, it fails to ensure security in certain scenarios. This is the first approach. The analytic and the optimal classification trees are maintain always the frequency nadir above the desired threshold, while the decision trees fail to ensure security in every scenario. They have a smaller accuracy than the optimal classification trees. Okay, so let's look a bit now how these techniques can be really put into actual operation, in real-time operation. So again, on the Rhodes Island, we have applied these technologies. You have the dynamic security assessment running every 15-20 minutes. So the way it does it is to receive the system state by the SCADA system of the island. Then you need to see what will be the dynamic security in the next 15 minutes. So you run a small short-term probabilistic forecast to estimate the wind power plant production and the PV production and demand. So you create a number of scenarios for the next 15 minutes. For each scenario, and based on the generators, you calculate the inertia. You calculate the available reserves for the next minutes based on the predicted demand and also the PV and wind power scenarios. And then you apply the optimal classification trees rules to see how the security of each scenario will develop. And if probability more than 1% as one scenario is insecure, and the state is flagged as insecure. Okay, so you need to see how the system will be secure in the next 15 minutes. You predict the several states of the next 15 minutes. For each of these states, you run your decision trees, optimal classification trees, and based on the results, you define if your system will be secure or insecure. So this is how the operator can let's say, predict, can see if the coming 15 minutes your system will be secure and secure in case you have the largest wind turbine being disconnected, okay? Where there's such a contingency or the contingency he chooses to check. Despite the good results and despite proving, of course, analytically or theoretically that this technique is relatively accurate in predicting the dynamic security, operators really rarely trust this type of applications. And because they don't trust black box models, they prefer the well-defined physical models. They have no guarantees of performance if there is no link to the physical models. And in fact, perhaps one of the main reasons that there is absence of extensive testing in a restricted environment. So they don't have any experience by testing these technologies in a realistic environment. So to face this weakness, we have designed a digital twin to build trust on the machine, to build trust on the machine learning DSA. So in this case, the DSA, the SCADA system of the DSO sends every minute the data now to the FTP server through the FTP protocol. The system state is the generators, active and reactive power, demand, weather conditions, renewable generation, etc. And then you have a digital twin, which is a dynamic model of the island, as you see there, which runs on the dynamic real-time simulator, which is also connected to a so it sends this state to two different settings. First, besides the DSA software, that it runs every 15 minutes, as you said, that sends every minute the data to an simulation software that runs with very detailed models every minute, okay? So it runs the simulations and provides the security metrics. And also it sends it to a digital twin, which runs on the real-time digital simulator. And it's connected with an industrial, the frequency relay, the same settings as the island. So the operator can assess the results of the DSA as they are performed by the DSA software with a very detailed real-time simulation that's connected to the actual hardware device and also by the very detailed EMT simulation with the detailed models. And he can run that for several contingencies and make sure that what he sees predicted by the DSA is also what the real-time simulation is providing. So let me perhaps run this simulation. In this case, you see that your dynamic security module, the dynamic security module has already predicted that the next stage will be insecure. Your relay is still in normal state. It has not operated. And now you have the data coming every minute. And for a particular case now, you see that the power system state is updated. So when it is stabilized, there is a simulation of the largest wind turbine being disconnected, wind park being disconnected, which is here. And then you see that your relay, sorry. So your relay now has, your relay, look at the relay, it will trip. They will trip by showing that this is the under frequency, okay? So in this way, at least the operator can make sure that the detailed simulations that he trusts using the RTDS coincide, I mean, have the same result as the DSA that he's predicted 15 minutes before. Okay, assessing the results, we can see now that we have evaluated the EMTP simulation software with 65,000 operating states and the demonstration of the real-time digital simulator for a total of 6 hours. The preventive actions have led to over 95% of reduction of the possible load setting conditions. There has been some weaknesses detected. The basic problem was that in the EMTP simulation, a number of cases that were insecure were misclassified as secure. And the problem is that during the training on normal operating conditions, the DSA tool did identify generators that were on shutdown procedure. So they were considering that these generators that were not still disconnected, but they were on shutdown procedure, their inertia and reserve were still present for the next 15 minutes. So they were counted as existing reserve and classified the system as secure erroneously, while the digital twin that runs operation with near live data could identify that these were insecure. So this has led to an improvement of the software of the modeling. So, I mean, even now the empty simulation is much more accurate. So that concludes my presentation. We have talked about system with high res penetration, island systems, and the new techniques that are required to include frequency security, economic operations. We have used optimal classification trees and to provide linear rules so they can be then easily implemented in unit commitment problems. We have proved that they have higher accuracy compared to conventional and also decision trees. We have looked at the problem of the reluctance of system operators to adopt such solutions, and we have applied digital twins that we believe can serve as advanced test beds for extensive and realistic testing under real life data to replicate the physical system and help operators gain trust in such data-driven techniques. So thank you very much for your attention, and I'm happy to answer any questions.
Thank you for the wonderful presentation today. So if you have any questions, and then please use chat window. And I think we already have one question from Petros. So Nikos, can you see the chat window?
And I will stop sharing, okay?
Yeah, of course. Yeah, you can stop sharing.
Okay.
And then there is like a chat icon on the bottom of the Zoom application. And if you click it, and you can see the chat.
Yeah, that's Petros asked a very nice specific question about the Greek code. If it includes requirements for grid forming capabilities for renewable units. I guess I don't think that at the moment there is such a provision for islands. I don't think it's also there is even for the mainland as a Greek code requirement. I'm not 100% sure, but I don't think although it is discussed, I don't think it's still a requirement to provide this type of services as grid forming units.
Yeah, thank you. And so I have just one quick question. So after, so you use the digital twin for acquiring the trust of the operators. You developed a machine learning based approach, and then you just compare between the machine learning results and then also digital twin results. And then actually the accuracy was kind of satisfactory. And then did you successfully acquire the trust from the operators in Greece? Still, they are skeptical for the machine learning approaches. What is the current status?
Yeah, this is not running for a long time to be sure that they have really developed trust, but difficult to answer. I wouldn't say that they are still using it extensively, but also, there are not so many incidents that threaten the security of the system, so that they can be. That's why they need to run simulations and be sure that analytical models that they trust can behave similarly using.
So the frequency of the event is kind of small number. So it takes long time to build a kind of trust from the operator, right?
Yeah.
Yeah,
exactly.
got it. And we have one more question, or two questions maybe.
Yeah.
Two questions in chat windows.
Could you please elaborate how the model parameters? Yeah, I think these are the ones provided by the manufacturers.
But that is usually confidential, right? Do you have like a detailed model or like a dynamic link library models only? What level of models did you get?
No, they provided some data for this island. This was
Okay, sounds really good. But this is not open to the public, right? Only within
yeah,
your
they are not
institution.
publicly available now.
Okay. And we have one more question about the digital twin technology.
I guess if you need some elaboration on my question, I guess the whole idea and concept of digital twin technology is building the most accurate and most real-time feedback system, right? Replicating it, and I guess how feasible is that, considering like I guess in layman's terms, that kind of like creating the matrix, and depending on how accurate you'd want to get. So I guess do the current levels of digital twin technology and representation actually meet your standards of what is needed to achieve your goals in this type of grid planning?
Yeah.
Or
Clearly, digital twins are also models, okay? And the models are as good as the model is, as good as the data the model is.
mhm,
So, I mean, the model itself might be inaccurate. However, it is important that digital twin models at least are linked to actual real-time data.
mhm,
So that's why they can, assuming that the model is relatively a good physical model, having the real-time data provides much more accurate results, right?
mhm,
And that's also is shown in this example that using the result as the example I said, when you compare the EMT simulations with the digital twin results, you could see that EMT simulations were wrong because they assumed that, for instance, your generators were online because they did not detect that the power was zero. But the So they thought as they were still running, although they were already slowing down to be disconnected, the digital twin could see that and take into account that this inertia did not exist in the coming minute. Okay, so
Okay.
a digital twin provides much more accurate results exactly because they are linked to real-time data.
Yeah, and then this.
Now, if this is satisfactory, if this is really the real world, okay, that's a big question now.
Yeah, I understand. Yeah, thank you for that.
Okay, thanks for the question. It's interesting.
Yeah, and how did you select 15 minutes? So we consider like 15 minutes later. So we consider the scenario 15 minutes later. And so, for example, if we predict the future status 15 minutes later, and then can the operator establish corrective actions? Like so that 15 minutes is from the time for unit commitment, or so how did you determine the 15 minutes? Because for example, the wind generation can change its active power output drastically even within 15 minutes. So, for example, if we consider the prediction accuracy of the demand, and then we cannot help selecting the 15 minutes. If we predict 30 minutes or 1 hour ahead, and then the error is too big. So we determine to select 15 minutes only. So is there any like a particular reason to select 15 minutes ahead?
Well, that was, I guess, that was given, but I guess 15 minutes gives you enough time to an operator to act, especially in islands where you don't have, big units. And also, predictions are for probabilistic predictions. So you get really several scenarios for the 15 minutes ahead. And you decide if your system is secure if 1% of your probabilistic forecast violates your limits. Okay. So it's a rather conservative decision on how you can assume that something is insecure, still is secure.
Okay. Yeah, thank you so much for this clarification. Yeah.
Yeah.
I think the time is almost up. So everyone, our next webinar will cover the different topic, like regulatory standards for grid code highlighting grid forming converters. And then we will be inviting Julia Matevosian from Electricity Storage and Integration Group in the United States as a speaker. So the webinar will take place on December the 18th, around 1 month later, starting at 11 a.m. our time. So the flyer has been already uploaded to RGPV tools. And so please stay tuned and enjoy the rest of your day. And again, Nikos, thank you very much for this very informative and very academic presentation today.
Thank you very much for the invitation, Coach. Thank everybody for listening.
Nikos. Thank you, Koji.
Yeah, have a great night.
Yeah, thank you,
Professor,
Koji.
Professor Koji? Sorry, did you need any work with the website of uploading anything with the webinar, anything right now? Just not.
Not yet. Yeah, I will talk about it later on. Yeah.
All
By
right,
email.
for sure.
Yeah. Mhm.
All right, thank you. Bye-bye.
Thanks, everybody.
Thank you.
Thank you, Max, to join.
Thank you, Professor.
Great. That's great. Thank you. Yes.